At this problem in section 1.5, number 33, says determine the open intervals on which the function is increasing, decreasing, or constant. If we trace our function from left to right, notice that it's decreasing, it's going down, right? It's falling. So that's how we know that our function is decreasing everywhere from negative infinity to positive infinity. And just to show you, let's use decimals just as proof that it is decreasing, right? From what x value on the left to what y value is it decreasing? The y's are decreasing. So it's from negative infinity to positive infinity. Notice how this is attempting to say that it's going off the page. There's no dot at the end. So we know that it's going off of the graph, which indicates that it's continuing on and on forever. So if we take a look at decimals, we see that if we click on this function, notice how the y values are decreasing. 5.3, we're in the 4s now, we're in the 3s. And even down here, notice that even though it looks like it's 0, it's really 0.023, right? And it's getting smaller and smaller, 0.018. And then even once we get across that threshold of 0, 0, we're going into the negatives now. So that's proof that it is decreasing everywhere. It's continuing on and on forever. This graph does not stop. All right, let's go to the next problem. We have writing an equation from a graph. Identify the parent function and the transformation represented by the graph. Number 57 is cubic, and it looks very similar to x cubed, but is the coefficient really 1? Not really sure, right? Because notice if you had to plug in a point for x cubed, f of x equals x cubed, you get 1, 1, right? 1 cubed is 1. However, look at this 1. It looks like it's more 1, 2. It looks like it's negative 1, negative 2, for example, not negative 1, negative 1. It's more so negative 1, negative 2. So one thing you could possibly do is to figure that out. We know that there's a point, for example, negative 1, negative 2 on the graph. So since the point is negative 1, negative 2, what we can do is plug those values into f of x equals a x cubed, because we know that the leading coefficient is not exactly 1, but what is it? So what we can do is solve for a by substituting in a point that we know that's on the graph, like negative 1, negative 2. So for f of x, we're going to put negative 2 since that's our y, equals a. We don't know what a is. We're trying to figure that out. We can substitute x with negative 1. Negative 1 cubed is negative 1. So what we have is negative 2 equals a negative 1a. We divide by negative 1, and we'll get a equals 2. Since a equals 2, we know that's our leading coefficient. Let's move on to problem in 1.8. Let's look at finding arithmetic combination of functions, but let's focus more on f / g of x. So when you see this /, just know that it means division. It's another way we write division. And what is the domain of that f divided by g? So what we can do is, first of all, let's write down the fact that we know that f / g of x is the same as f divided by g of x. This way over 4x minus 5. So that's really the answer to this f divided by g of x. But the question is, what is the domain? The domain of f divided by g of x, which is x squared over 4x minus 5. Notice that this is a denominator, so we know that we don't want x to equal something that will cause our denominator to actually end up equaling 0. So that's why we set the denominator to 0, or you can say we do not want this denominator to equal 0, and solve for x to figure out what x value will make it 0. So we can add 5 to both sides. That cancels out that. Then we have 4x cannot equal 5, and then we can divide by 4. So we know that we do not want our x to equal 5 over 4. So what does that mean? All real numbers except, all right, you can say all real numbers except x equals 5/4. Or you could write it in interval notation like negative infinity to 5 over 4. Parentheses, because we do not want to include 5 over 4 in the domain, since it would cause the denominator to equal 0. Union 5 over 4 to infinity. Alright, let's go to another problem. Let's try something like number 11. Let's look at number 9 first. Alright, as you can see here, all real numbers except 5 over 4. But let's go to number 11, x squared plus 6 over this square root of 1 minus x. X squared plus 6 square root of 1 minus x. So again, this equals f of x divided by g of x, which equals x squared plus 6 over the square root of 1 minus x. Well, notice that this square root is in the denominator, so we definitely don't want x to equal something that will cause it to be 0. And that's kind of obvious what it is, because it's just 1 minus x. It's obvious that we don't want x to equal 1, because that would make the denominator equal 0. But we also don't want numbers under the radical to be negative, because we do not want to go into we're not in the imaginary world system right now. We're in the real number system. So that's why we, in this case, since it's a radical and in the denominator, we'll set what's under the radical 1 minus x to equal greater than 0, not greater than or equal to 0, because it's in the denominator. And what I'm going to do here is just add x to both sides. If I add x, then my x is already on one side by itself. This means x has to be less than 1 to work. So numbers that are less than 1 for x will work in here, not the other way around. So all real numbers such that x is less than 1. For example, 0. 0 will work in here because 1 minus 0 is 1. Square root of 1 is 1. That's fine. But if we took a number like that, it was more than 1, 2, that would be an issue here because of it being negative under the radical. Another way to write this would be from negative infinity to 1, right? We don't want it to equal 1. That's why we do not have a bracket. Or set builder notation, x such that x is less than 1. Alright, we're moving on to another type of problem. This one, use the graphs of f and g to evaluate the functions. We have two graphs here, graph f of x and graph g of x. So let's take a look at number 41, where we have f of g of 2 and g of f of 2. Now, f of g of 2, we know that g of 2 is the inside function. So what we're going to do is go to the g function first. G of 2 would be 2, 2. If we intersect with the graph, we have 2. Now we need to go over here where there's a 2 and notice that that point is 2, 0. So the answer is 0 for this problem. So g of f of 2. F of 2 is the inside function. If we wrote it as g parenthesis f parenthesis 2 close parenthesis, f of 2 would be the inside function. So we go to f of 2 first. Again, we just said it. When x equals 2, y equals 0 here. But then that will cause us to go to 0 on this graph because that's g of x is our outside function, and when x is 0, y equals 4. So the answer to that one is 4.